Hi everyone, I am Shorodip Chakraborty, and today I'll be presenting our work on posterior course set with kernelized time discrepancy for model-based reinforcement learning. This is a joint work with Amrit Singh Bedi, Alec Kopel, Brian Sadler, Pratap Tokekar, Furong Huan, and Dennis Panosha. So we start with the exploration-exploitation dilemma is a very important challenge in reinforcement learning, especially if we want to exploit the usual place or explore a grand opening is a very important question to ask. And uh, to solve this question, we need a very efficient representation of the uncertainty or a prior belief over the environment, both of which motivates us towards a Bayesian setting of reinforcement learning, which is the focus of this talk. So uncertainty and Bayesian RL methods involve a model-free Bayesian RL, which basically represents a posterior distribution over the Q network or the policy network. However, they suffer from sample inefficiency and hence are applicable to mainly simulation settings. On the other hand, model-based Bayesian RL maintains a posterior distribution over the transition or a reward function, and they are highly sample efficient, and they have achieved a huge success in real-world in reinforcement sequential decision-making tasks. But to implement or to apply model-based Bayesian RL, most of the people have applied approximate Bayesian methods, which involve an ensemble, which gives an inexact notion of uncertainty, and also it requires solving the inner optimization with multiple ensembles, which is computationally tractable with less theoretical guarantees. On the other hand, posterior sampling reinforcement learning is an exact Bayesian method. With posterior sampling, it is computationally tractable and it has very good provable guarantees with Bayesian regret. So just let's review that what exactly posterior sampling reinforcement learning is with model predictive control. So in the first step, we sample a transition and a rewards model from the posterior distribution. And then the agent's current state with the transition and the rewards model, it goes to an MPC, which actually optimizes this expectation over the transition and reward. And finally, it chooses the optimal action for that state, and that passes through the environment, which then gives a new state and a reward based on the true or the ground truth transitions and reward, which then we append to the dictionary and then update the posterior and repeat the process. Recently, Fan et al. In ICML 21, they showed that posterior sampling reinforcement learning with MPC model predicted control actually can outperform all existing benchmarks using model-based and model-free for various continuous control environments in Mojoko with great benefits in sample efficiency. So this raises the question that then is PSRL enough to solve the exploration problem in continuous control problem that we were discussing about? So since I'm asking the question, the answer is no, it does not. And let's discuss some of the challenges and bottlenecks in PSRL. So one of the major challenges, the large scale training bottleneck. So as we discussed that over the iterations, we append more and more state action S prime are tuples to the dictionary, and the dictionary size can potentially grow to infinity with for large scale environment, which requires a huge amount of samples. So what happens because of that? The posterior representation complexity becomes unbounded. So what do we mean by that? Let's try to understand through a simple example. Let's try to take an example for a Gaussian processes. And we know that GPs are a very good way to represent posterior distributions. And we know that the posterior representation for a GP is mean and the covariance function, which requires the inversion of a kernel matrix, which is again dependent on the number of samples, or basically in that case n. So and it requires inversion, which means the complexity goes to order of n cube. So even a simple Mojoko task, it requires maybe the sample complexity can go to 10 billion, which is highly intractable. And the third thing is that there is a high computational bottleneck because of this unbounded posterior representation. Even the sampling gets hampered, as well as this solving this expectation, which is over the transitions and the reward, gets hampered as well. Another challenge lies in the strong assumptions that had been in the prior literature. So, in most of the prior literatures, they have assumed that the transition or the reverse model lie in a symmetric class of distribution or a Gaussian densities. In some prior works, the analysis or the regret analysis or theoretical analysis has been done, keeping into mind that with linear kernels, that the transition lies in a linear kernel space, which is not very practical in more complex problems. Another issue has been some Lipschitz assumption on the value function with no explicit dependence on the horizon and the Lipschitz constant. So that has been a point of concern in some of these earlier assumptions. So to summarize that, we get two major challenges. One is the large scale training and unbounded posterior complexity. The second is the strong assumptions on the transition value function class. So under this assumption, we ask the question that is it possible to achieve an explicit trade-off between the complexity and the regret or some theoretical notions without restrictive assumptions in the model class in for continuous state action space? So one can say, yeah, we can do that. We can simply do an online compression and dictionary. So we review some of these online compression methods, which can be random sequential thinning or different posterior variance based thinning. But the issue is that most of these methods either lack theoretical guarantees or they have only closed form for Gaussian distribution, which is again falling back to the same problem. And if we do not take care of this, it can significantly hamper the regret. So for that, we propose a posterior course set based method in model based PSRL. And we are the first to propose such a method, which is an online dictionary compression based method in model based PSRL. So to begin this, first we try to motivate that how we formulate the dictionary compression as with an IPM or integral probability metric based formulation. So we try to select those samples based on which will represent the distribution and such that this divergence term is actually minimized from the ground truth. So let's go a little bit into the divergence term more. So we see that the divergence term requires when we expand this, if and we can, and this is a standard expansion for the integral probability metric. So we can see that that it actually needs an integration under the ground truth p star, which is never accessible to us, and it requires a supremum to be solved, which becomes computationally hard. But with the advantage of Stein's identity, actually, and assuming this function to be in the Stein class, we can actually get rid of both these terms, and we can get a closed form solution of this divergence or discrepancy in terms of kernelized Stein discrepancy due to the Stein's identity. So once we understand that if we can get a closed form solution under certain conditions of the KSD, then the question comes that how do we apply this to our current setting? So our proposed algorithm is like, so whenever we append this dictionary and then we apply this KSD based thinning to our dictionary and we compress the dictionary or the distribution characterized by the dictionary. So how do we do that? So first of all, we compute the difference KSD till a point of time. So let's say at the kth episode, we have the dictionary DK and we compute the KSD for that DK, or lambda DK plus 1 is just a posterior is just the distribution PK or RK, which is characterized by the dictionary. And the closed form will depend on the Stein kernel, which is a function of two terms, Hi, Aj, which are basically the state action S prime tuples in our case in reinforcement learning. The second term is we remove the least influential point. So the idea is that whenever we will remove some point, the KSD will increase, because when it is exactly the true distribution, it is 0. So whenever we remove some points, it will increase. But we want to bound this increase, which is actually done through this budget parameter. And finally, once we do that, we output the thin dictionary, which is then passed on, and the iteration continues. So this is how we incorporate the KSD-based compression intelligently into our system. But then the question comes that, okay, we have incorporated KSD into our system, but how does this give provable guarantees, or how does it connect to the notion of regret? How can we show that with KSD compression still we can have some sort of a regret guarantees, or how do we have an explicit trade-off? So this was another very interesting part of our work, where so what we do is we try to we first denote the base regret, which is a standard definition of base regret, and then we try to break it down into a difference between the future value function, which can be represented as a total variation distance between the transition and there we actually upper bound the total variation distance with the Stein discrepancy, and here comes the Stein discrepancy. So once we have brought the distance between the two distribution in the as a Stein space, you can understand, as we have discussed prior, that how I can actually compress the dictionary and how the entire thing can fall back into this. So for more details, refer to our paper and lemma 4.1. So this was the explicit connection that we actually developed, that between Stein and regret. And once we have brought into Stein, we actually upper bound the Stein with the number of episodes, and we finally derive the base regret with that upper bound, which is in the order of d, the dimensionality of the state action space, horizon length, and t is the total number of time steps. Now, you very interestingly, you will see that for the first time in this analysis, or in this kind of analysis, we bring a flavor of explicit complexity parameter, or which kind of a dictionary complexity, which tells how much, like what will be the growth of the dictionary, how we can control the growth, and how it can affect the regret. So this is the first time that this kind of a flavor of analysis has been done. So here fk denotes the course set size growth, or the dictionary growth rate, and mt is the complexity or the course set size. Alpha is the tunable parameter. So you can see that when alpha is 0, we get a linear regret. So basically it's almost like we keep the dictionary unbounded and everything, we don't control anything. But when we control it to a certain extent, when alpha is 1, we get the best known regret for a PSRL, and with relaxed condition. And this trade-off is actually very unique that we had brought in the analysis with kernelized time discrepancy. Now we try to see that can posterior compression with KSD provide a trade-off empirically as well. So we perform this experiment on various Mojoko continuous control environments, and we see that it actually matches the best known, or even sometimes improves over the best known or the state-of-the-art MPC PSRL in terms of sample efficiency, and basically in terms of average reward. So we get higher reward or equivalent reward, but we get drastically reduced dictionary complexity. So we can achieve very high reward, but with a very low number of sample storage or dictionary complexity. So to understand, let's maybe zoom into one of this environment and see that. So you can see that KSRL actually is able to achieve the maximum average SOTA reward with around 75% drop in model complexity, which is really huge. And then we also do different types of ablation-based studies for our analysis. For example, we see that how is the performance in terms with PSRL when there is a fixed restriction on the buffer size. So if we have, let's say, for some tiny edge devices, it cannot take beyond that. So either we use random thinning or sequential thinning, and you can see definitely KSRL improves over that. Similarly, we see the comparison of posterior variance convergence with the time steps when we are doing compression and when we are not doing compression. So we see that even we are doing compression, ideally the posterior variance should have used, but since KSD is doing intelligent compression, it converges actually almost equivalently with PSRL. And finally, we also see, since the computational bottleneck is less, it actually KSRL requires much less wall clock time than PSRL. So these are this was the main part of our work. Now, as a part of future work, we focus on deployable RL. How can RL be made more deployable? One main point is large scale training. So how KSRL based compression can help in complex and large scale robotic tasks with provable guarantees is something that we want to do as a part of our future work. Similarly, if we can have an efficient posterior course set, can it reduce the use of billion per parameter decision transformer and maybe a step towards energy efficient RL? And finally, when there is a tiny edge device which does not have a huge buffer size, can we use posterior course set and see some applications on like tiny edge device and maybe build a tiny edge RL phenomenon? So this was all from our side. These are some of the references. Thank you.